In the previous class, in lecture number 1, we started the discussion on the review of transmission lines pertaining to RF applications. So as far as RF is concerned, transmission lines denote any pair of conductors whose length is effectively comparable to the wavelength of the wave or the wavelength of the signal that is essentially being carried in the transmission line from one end to the other end. So we saw that the transmission line arrangement in its simplest form was something like this: a source and load. And we had actually defined the load as the reference point, and we had said that going away from the load towards the source is positive L, which is the opposite of the x direction. So at the load point, we consider the origin, that is L equal to 0. So essentially we saw in the previous class that the solution for the transmission line voltage and current is effectively a pair of waves, that is one traveling from the source to the load and the other traveling from the load back to the source. This is of course a steady state solution, which means that this arrangement has been on for a long time, because for the reverse wave, that is the wave from the right to left, would only exist if the original wave that is going from the source to the load hits the load at least once. That means if there is a wave that is traveling from the source to the load and has not yet reached the load, then obviously the question of the backward wave does not arise. So the backward wave is also called as the reflected wave, and using that we had defined that there is something called as reflection coefficient, which is nothing but the voltage ratios of the reverse wave to the forward wave. And what is most important to note is that the voltage and current are not just functions of time, but they're functions of position also. However, for the time being, we are not that bothered with the time aspect. So we are assuming that this transmission line is a lossless line, and that will be our assumption for most of this course. Beta is the propagation constant. V plus and V minus are constants which are there as a result of the solution for the differential equation of the voltage and current. So here Z0 is the characteristic impedance, and if you recall, in the last class we had defined this to be R plus j omega L divided by G plus j omega C. But for a lossless line, it should not have any resistance, and the insulator that is existing between the two conductors should have zero conductivity. So that means for a lossless line, both R and G are essentially 0. So that means for a lossless line, if R and G are both 0, then the characteristic impedance is under root of L by C, which is nothing but a real quantity. So lossless transmission lines always have a real value of Z0, or the characteristic impedance. This is something very important to know. So if you ever go to the market to buy a transmission line for any of your work, or you are making a transmission line yourself, so a good lossless transmission line should have a real characteristic impedance. So coming back, we have these two equations which denote the voltage and current on the line as a function of the position. So with this, we can actually define that if the load impedance is ZL and the line impedance or the characteristic impedance is Z0, in that case, we can also define Z of L, which is nothing but the impedance at any point on the line L. So Z of L is nothing but the ratio of the positional voltage and current. So what can we say? We can simply divide these two. So I can take 1 by Z0 common in the denominator, which would make Z0 come over here. So we can take the first term, that is V plus times e raised to j beta L, common from both numerator and denominator. So that would make it this Z0 1 plus. So the second term will now be V minus by V plus e raised to j 2 beta L. Is that fine? Yes, we can do that. So effectively we can write divided by 1 minus two beta. Yes, this is something that we can write. So we already know that V minus divided by V plus is indicative of the reflection coefficient at the load, and that we had designated as gamma suffix capital L. So using the Euler entities and the equivalent trigonometric forms of this complex exponential, and also the fact that in the last class we had defined gamma L as ZL minus Z0 divided by ZL plus Z0, you can in fact substitute this over here, and using the trigonometric equivalents of these complex exponentials, you can actually show that the impedance Z of L at any point on the line L is nothing but this quantity, Z0 times . So this is a very important relationship. What we derived? We have derived that Z of L is effectively Z0 times ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. So this relationship is called as the impedance transformation relationship. Why it is called impedance transformation is because at the load end of the line, the impedance is ZL, or the load impedance. And because of the fact that the line has a distributed nature of impedance which gives rise to the characteristic impedance, there will be some value of ZL or different values of ZL as you move along the line. So there will effectively be these impedances, or the impedance at any part of the line would change as a function of L. So effectively there is one load impedance and that sort of gets transformed as you move along the line. More importantly, for a practicing engineer, it is important to note that the impedance transformation relationship gives you the means to calculate the impedance at any point on the line, so long as you know the load impedance, the characteristic impedance, and the position. So using this relation, you can calculate of course beta also you need to know, but beta is a trivial quantity which is nothing but 2 pi by lambda, where lambda is the wavelength of the wave inside the transmission line. So this is a very trivial quantity and for most cases you would know this. So now let us see some interesting properties of this impedance transformation. Now suppose I have a transmission line. Let's say I do not know what is the load impedance, but I know that there is some point where L equals some value L1, and there is some other point L that is equal to L2, such that these two distances or these 2 points are separated by a distance of a half wavelength. That means since the positive L is to the left, this point would be L1 plus lambda by 2. That is to say, the distance between these 2 points would be half a wavelength. Half a wavelength of what? Half a wavelength of the wave that is actually traveling in the line. So the question now is, if the impedance at this point is some Z of L1, what can be said about Z of L2 in relation to Z of L1? So Z of L1 we can write it as this: Z0 ZL plus JZ0 tan beta L1 divided by Z0 plus JZ1 tan beta L2. Sorry, L1, not 2. Now, if I want to write for Z of L2, what do I need to write? So L2 is nothing but L1 plus lambda by 2. So what you will get is this: Z0 times ZL plus J Z0 tan beta L1 plus lambda by 2. divided by Z0 plus JZL tan beta L1 plus lambda by 2. Let us open this bracket. So beta of L1 plus lambda by 2 would give me beta L1 plus beta lambda by 2. But we already know what beta is. Beta is 2 pi by lambda. So therefore beta lambda by 2 would be what? So this would be nothing but pi. So effectively this would reduce to something like this. So tan of pi plus anything would be tan. So this is nothing but Z0 ZL plus JZ0 tan beta L1 divided by Z0 plus JZL tan beta L1. So this is exactly the same as Z of L1. So what this means is, if you have a lossless transmission line and you move from one point to another point which is exactly half a wavelength away from the first point, then the impedance would be the same. That is like saying the impedance is effectively repeating after a distance of lambda by 4. So therefore, let us call this as golden rule number 1 of transmission lines. That is, the impedance repeats every lambda by 2 distance along a lossless transmission line. So this is golden rule number 1. Now let us do another study where we have a transmission line. Let us say at some point L equals L1 and we take another point L equals L2, but this time L2 and L1 are separated by a distance of quarter wavelength or lambda by 4. So that is like saying L2 is L1 plus lambda by 4. What would now happen? Well, let's start from where we started. Z of L1, we are starting the same way as we started for the previous case of lambda by 2. So this would be Z0 times ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. L1. So likewise, Z of L2 would be Z0 ZL plus JZ0 tan beta L1 plus lambda by 4 divided by Z0 plus JZL tan of beta L1 plus lambda by 4. So this would now reduce to Beta times lambda by 4 would be what? It would be pi by 2. So you can use your trigonometric identities and effectively show that this, because of this pi by 2 plus theta, you're going to have a very interesting result, and that is you will see that z of L2 is this. Does this look familiar? Yes, it is 1 by ZL1. So this is Z0 square divided by Z of L1. So, while this is indeed a much simpler expression as compared to what we had early on, this is still not as interesting as one would have hoped it to be. This result probably doesn't look as interesting as one would have hoped it to be. So the question is, can we do something and make it even more simple? Well, we can do that. We can take one Z0 to the left. So what we will have is Z of L2 divided by Z0 is equal to Z0 divided by Z of L1. Now, let us introduce a new convention or a new term that is called as normalized impedance. And that is a dimensionless quantity which is indicated by small z. And that is nothing but any impedance capital Z divided by the characteristic impedance. So therefore, if we now write this above expression in terms of the normalized impedance, which is a dimensionless quantity, we will see that small z of L2 is equal to 1 by small z of L1, because here Z0 is on the numerator. So with this, what we see is, if you move along a lossless transmission line along a distance of lambda by 4 or a quarter wavelength, what you will see is that the normalized impedances effectively become inverted, not the actual impedance. The actual impedance has units of ohms, so therefore inverting of the impedance would not remain it to be an impedance quantity anymore. But normalized impedance, since it is a dimensionless quantity, it will be inverted. So therefore there is no problem if a dimensionless quantity is inverted, because there is no change of units. So therefore with this we propose the golden rule number 2. So the golden rule number 2 would be stated as moving by a distance of quarter wavelength along a lossless transmission line causes the normalized impedance to invert itself. So here the word normalized impedance is very, very important. Not the absolute impedance. It is the normalized impedance. So we have established the golden rule number 1 and golden rule number 2 of lossless transmission line. Now let us look at another golden rule. Let us say we have a line where the line is terminated with a load impedance ZL. The line has a characteristic impedance Z0. But the load and the line are matched. Matched means what? ZL is equal to Z0. So in that case, if we consider the impedance transformation relationship Z of L, that is nothing but Z0 ZL plus JZ0 tan beta L divided by Z0 plus JZL tan of beta L, and that is, if Z0 and ZL become equal, then these two would effectively cancel out, the numerator and denominator fully, and then all you would have left is Z0. So that means the line impedance or the impedance seen at any point on the line is always the same, that is Z0. So with this we propose golden rule number 3, which is probably the simplest of all the rules that you have come across of all the 3 so far. That is, in a transmission line where the line and load impedances are matched, the impedance seen at any point on the line would be constant, which is nothing but the characteristic impedance of the line itself. So these are the 3 golden rules of lossless transmission lines, and it is better if you are familiar with these golden rules, as they would make your life a lot easier. Now let us go back to the expression for the voltage as a function of the line length L, which is nothing but this quantity. Let us now take a look at this voltage quantity and a little more about how it changes along the line. We now know, or rather we have some idea of how the impedance varies along the length of a transmission line. We know the impedance transformation relationship, through which we saw some 3 golden rules. And even apart from these 3 golden rules, using the impedance transformation relationship, you can find out the impedance at any point on the line. But the relationship, or rather the transformation of voltages and currents, is not all that clear at the moment. So therefore, let us look at this expression. And what we will do, we will simply take the first term common and open up this bracket. This will be 1 plus V minus by V plus times e raised to minus j 2 beta L. So therefore, we can write this again as this plus, now this ratio of V minus by V plus is nothing but the load reflection coefficient gamma L times e raised to minus j to beta L. Now this is a complex term. This is a complex term. In general, even V plus can be a complex term. But what about gamma L? We know that gamma L is nothing but ZL minus Z0 divided by ZL plus Z0. Now ZL can be real, it can be imaginary, it can be complex. So therefore gamma L in general is a complex number. So we can represent gamma L in the polar form where we have its magnitude and some phase, let's call it as phi L. So therefore, what we will get is now this e raised to j phi L and this e raised to j term can be combined and written as phi L minus 2 beta L. Is that fine? Okay. So with this, we now have some kind of a relationship, and from this, let us try to see what the nature of VL is. One thing is for sure, VL is a complex quantity because of all these terms, which in general are complex numbers. So my question therefore is that, can we then do some analysis which is a little bit more simple? Can we do some analysis which is a little bit more simple in the sense that rather than looking at the absolute nature of VL, can we look at the magnitude of VL? That's going to give us some bit of an easier analysis. So if I take the mod, what I will get is mod of V plus, because the mod of e raised to j beta L is always 1, times the mod of this entire quantity. So this is the magnitude of V of L. Now this quantity, that is mod of V plus, this is a constant. What is actually varying is this quantity, because it is varying as L changes. it varies with L length. So therefore, the question now is, what can we say about this variation that will give us some idea about the magnitude of this V of L? Well, what we can do, we can ignore this V plus mod for the time being and concentrate our efforts on this term, 1 plus mod gamma L times e raised to j of phi L minus 2 beta L. The question is, this in general is a complex quantity. In general, this is a complex quantity. So, can we represent it in some form which will give us a clearer idea of VL? Yes, we can represent this 1 plus this term as a kind of vector addition on the complex gamma plane. So 1 on the complex gamma plane, now 1 is real, so therefore if this is the origin, 1 would look like this, a unit magnitude. Now this one vector is done. This second vector is what? Mod gamma L times e raised to j of phi L minus 2 beta L. So this particular vector, if you look at only the second term, this indicates a complex number or a vector that has a constant magnitude, but its phase changes with L. So therefore, a vector that has constant magnitude but changes its phase would trace out the path of a circle. So therefore, if I want to add, suppose at any point of time, the second quantity or the second vector is over here, then its magnitude will be mod of gamma L and its phase angle would be phi L minus 2 beta L because it is in the polar form, and this would actually trace out the path of a circle. Depending on what the value of L is. So the question now is, how does this tip of the vector change? Now, before we see the tip of the vector, let us not forget that these two vectors are to be added. So therefore, if the unit vector is over here and the gamma L vector is this way, then the resultant of these two vectors would, as per the triangle law of the vector addition, would look like this. Right? Yes. Now in this expression, which are constants and which are variables? Well, V plus is a constant, as we already know. 1 is a constant. Gamma L is a function of ZL and Z0, which are constant once the load impedance and line impedance are fixed. They don't change. Likewise, even phi L is a constant. Beta is a constant because it depends on the wavelength, and L is variable because we can change our position at any point on the line. So therefore, let us say if L increases, that means I am moving from the load towards the source. So therefore, if L increases, phi L minus beta L would decrease. So if L increases, then phi L minus 2 beta L, this quantity would decrease because L is increasing. That means the phase angle which it makes with the real axis would also reduce. So therefore, the vector would essentially rotate clockwise. So this is denoting the clockwise movement. Likewise, if L reduces, then phi L minus 2 beta L as a whole quantity would increase. This would increase. And that is like saying you would move counterclockwise. Like this. The tip of this vector would move like this. And when L is increasing, it would move like this. So therefore, this is called movement away from load or towards source. This is movement towards load, that is away from source. So this is a very, very interesting phenomenon. Now, what we saw was that there is a circle, and there is this resultant vector. Now the question is, when would this resultant vector have the largest magnitude, and when would this resultant vector have the smallest magnitude? Well, as you can see, just by looking at this vector diagram, that the length of this resultant vector would be the longest if it is along the real axis and if the tip of the vector is over here. Likewise, the length of this resultant vector would be least when it is along the real axis but its tip is over here. Because depending on what is the magnitude or what is the orientation of this gamma L vector, sometimes the vector may come here. So this would be the minimum. So therefore we can say mod of V of L will be maximum when this phase angle is either 0 or 2 pi or 4 pi or any even multiple of pi. Likewise, V of L will be minimum when this angle would be either pi or 3 pi or 5 pi and so on. So this is how it is. Now, we can say that this point therefore corresponds to mod of V of L maxima, and this point corresponds to mod of V of L minima. Right? So when VL is maximum, let's call it as mod of VL max. So that is nothing but mod of V plus times mod of 1 plus mod gamma L times e raised to j 2n pi. What would that be? It's nothing but V plus times mod of 1 plus mod gamma L. So now since mod of gamma L is always real, we can replace this with a normal bracket. We don't need to write mod anymore. Likewise, V of L minimum will be V of V plus mod times 1 times mod of 1 plus mod gamma L times e raised to j 2n plus 1 pi. So this would cause it to have a minus sign. Therefore, this will be V plus times 1 minus mod of gamma L. So if I take a ratio of the maximum to minimum voltage magnitude, that is VL max by V of L min, that would be the ratio of these two. V plus and V plus mods would get cancelled and we would get 1 plus mod gamma L divided by 1 minus mod gamma L. This ratio is termed as a quantity called rho and is called as Vswr, or the voltage standing wave ratio. The voltage standing wave ratio. Why standing waves? The reason we will see shortly, probably in the next class. But it is important to know that this is what happens. So now let us see one more very interesting result. So we saw V of L max happens when phi L minus 2 beta L is 2n pi. And we saw that the minima in VL happens when phi L minus 2 beta L is an odd multiple of pi. Now let us say I have a transmission line. At some point L equal to L1, I am observing maxima. And at some point L equal to L2, I am observing minima. Then can I say what will be the distance between these 2 points? So therefore, let us substitute them. So here L will be L1. This will be sum 2n pi. Likewise, phi L minus 2 beta L2, because it's the minima, it will be 2n plus 1 pi. So if I take the difference of these two equations, if I subtract the first equation from the second equation, what I will get is the following. I will get and that will be equal to pi. 2n and 2n would get cancelled. So that means L1 minus L2 would be equal to pi by 2 beta, and that is nothing but pi divided by 2 into 2 pi by lambda, which is equal to lambda by 4. Now this is another very interesting result. The distance between a voltage maxima and a voltage minima is always lambda by 4. the distance between voltage maxima and voltage minima is always lambda by 4. Similarly, you can prove that the maxima of the voltage and the minima of the voltage, they repeat every lambda by 2. This you can prove. I leave this to you as an exercise. So if this is Vmax, this is Vmin, and this is also Vmax, you will see that this distance is lambda by 2. Sorry, this is lambda by 4. But this big distance is lambda by 2. This proof I leave it to you as a simple exercise. So in today's class, in this particular lecture, we saw more about the behavior in transmission lines, that is the impedance transformation relation. We also saw some interesting properties of the impedance transformation relation in regard to lossless transmission lines. And thereafter, we saw a pictorial representation of the voltage on the transmission line in the vector form, and that gave us some idea of the voltage maxima and the voltage minima on the line, and the ratio of the maxima to the minima is called as the Vswr. And we finally saw that on the line, any maxima and minima, or rather two successive maxima and minima, are separated by a distance of quarter wavelength or lambda by 4. We shall continue from this point onwards in the next lecture. Thank you.